today's video we'll be solving this question of is the given graph bipartite, and after solving this question we will also be able to solve another question which runs on the same code, which is by the name of is graph contains an odd cycle. So I'll explain you why. Let's first learn what is bipartite graph. So in mathematical field, a bipartite graph is a graph whose vertices can be divided into two disjoint and independent sets U and V. So it's like you're dividing the entire graph, which is, for example, in this case is jumbled. You divide this into two sets. Okay, so you divide this into two sets, let's say a set of red nodes and set of blue nodes, such that the set of blue nodes has at least one, it can have more than one of course, but at least one edge connecting it to another set, right? So A is connected to 1 and 3, so that's how we define the connectivity, right? So this bridge is connected to, this nodes are connected to this red nodes via this bridge. So every node of B set must have at least one edge towards that of the red vertices. So set of red vertices. So that's the case, and there is another case, like there cannot be any edge among nodes present in the same set, meaning this blue edges, blue vertices would not be connected to itself no matter what. So it's like, you see, there are no edges present between any of the two red nodes. Similarly, there are no edges present within, like in between any two blue nodes either. So that's how we define what bipartite graph is. Now it's a very common observation that we can do, that if you can draw a distinct line separating the vertex such that these are not, one is not connected to another. For example, if you were to divide 0, 1, 3, 2, how would you divide? Such that, for example, you cannot divide it like making a distinct line over here, because 3 and 2 cannot have an edge among themselves. So you check the two nodes which do not have an edge connecting each other. So we divide that into, 3 and 1 would definitely not be in a different kind of sets, because 3 and 1 aren't that directly connected. So if we divide this based on 3, 0 and 1 and 2, will it work? Let's see. 3, 0. No, it won't work because this is having an edge. So we'll divide this into 3 and 1 and 0 and 2. Will it work? Yeah, it will work, because 3 and 1 do not have any edge between themselves. Similarly, 0 and 2 do not have any edge between themselves, while 0 is connected to another set, 3 via this edge, and similarly to 1 via this edge, and 2 is connected to 3 and 1 via two different edges. So we can tell that this graph can be divided into two sets such that both the sets are connected to each other, given they are not connected among themselves, like there are no edges present between the nodes of the same set. Okay, and now can we do this in this graph? Let's see. The options that we have is 3 and 1, fine. So what we can do is we can have 3 and 1 in one different set, and then we just have to make the 0 and 2 in a different set. But can we do that? No, we cannot, because 0 and 2 are connected. What did we say? If we divide the nodes into two sets, there cannot be any edges between the nodes of the same set, right? So if we make 0 and 2 combinedly into a different set, we cannot have an edge connecting 0 and 2. So 0 and 2 can definitely not be in the same set. Can it be in a different set? Let's see. If 0 is in this set and 2 is in this set, then okay, fine, 0 and 2 are connected, but then 2 is connected to both 1 and 3, and similarly is 0. So can we place 3 and 1 in either of the set? No, we cannot. Right, we cannot, because if we put 1 and 3 in the set of 0, then again that violates the property, as in 0 is connected to the same vertex, like the vertex belonging to the same set via this edge. And similarly, if we could keep 1 and 3 in this set of 2, then also the same rule is getting violated. So that's how. So if a graph contains, so basically the rule is, if the graph contains an odd, it's the observation of course, if a graph contains an odd length cycle, you cannot divide it into two sets, such that both the sets are satisfying the bipartite graph property. And why so? Because we allowed colors to it. Okay, so if we allowed, let's say, color red to this and yellow to this, and another, we have just two colors remaining, so we have to color the entire graph with just two colors, such that no adjacent nodes are having the same color. I mean, that's another definition of bipartite graph. So can you color, for example, this is what we learned, right? We are dividing it into two sets of color, red and blue. So can we divide this graph into two sets of two different color, let's say, such that no neighboring edges are the same color. So in case of odd length cycle, that's mathematically not possible for us to do it. Why? If we color this red and if we color this blue for it to be differentiated from this node, we cannot color this with any of the colors, because if we color this with red, then it's having a violation with the node 0, because two neighbors cannot have the same color, of course. So, and if we do that with blue, I mean, it's having the same violation with 3. So we cannot do that. So basically, in an odd length cycle, you cannot color the graph in such a way that all the neighbors have different colors. So that's how we reduce this problem to a problem where we detect the odd length cycle. If there are any odd length cycle, then that's not mathematically possible. We're not even detecting that. We're just allotting colors to the edges. And if we check that the edge we are coloring to is same, if the edge we are coloring to is having the same color as its neighbor, then that's not possible. And we'll do this using DFS. After seeing the code, you'll pretty much understand what I'm doing. So we are given with a adjacency list here. So the input format is this, and we'll be going forward coding it. So let's take up the size. Do we have to take? Yeah, we do have to. And this time we'll, instead of having a visited array, we'll be having a color array that will tell the color of each node. So initially all the nodes are in colors, will make the SS1. Okay, fine. Graph, right? So in case of graph, I prefer using a notation of v vertexes. So that's all. I'll go forward here as well. And now we'll simply do the DFS for it I is equal to 0, because this can have a disjoint component also, right? We're not given, but yeah, this can have the disjoint. I mean, I've done the normal, what do you say, a DFS, and it threw you an error, so it might have this disjoint component as well. So we'll go forward. If it's not visited, is only when we do the DFS call. If not visited means color of I is -1. That's how we track it's visited or not. And if DFS of I, but else are we passing color and graph is equal to false, and we return false, else we return true. Okay, but now this catch here wherein we have to pass the color that we are using to color this ith node, right? Initially, if you're starting with 0, let's say, then we'll have to color 0 with some, let's say we are giving that a color 0. Okay, we're giving it a color 0, and since we have to color it in two different colors, we're using the concept of either coloring it with 0 or 1. I mean, it's easy. You can do it with string operation also, or any other thing for that matter, but it's easier to go with 0. You'll understand it in a while. Why is it so easy? Because it's easy to code basically. So private bool DFS and source. Okay, fine. Int color. This is the color that we are coloring the source node with, and vector int with the adjacency. So we'll name this as ADJ, and then we are coloring the source node with the color. Okay, now we'll go to its adjacent auto ampersand I in adjacency of the particular node. If color of I is equal to -1, then if DFS of I and not color. Now why did we use not color? Because let me explain that in a while. If it's a false, it'll return false. Now why did we do that? First of all, let's see that, because see, if you're coloring this with 0, like the first node with 0, then the first neighbor of 0 is 1, so we'll definitely color 1 with what? 1 with a color that is not the same color as the source node, right? So we'll color that with 0, 2, and not of 0 is 1, so we'll color that with 1, and then again we go to the further node, like to 2, and we'll make sure that we do not color this as 1, like the same color, so we'll color this with 0, and then again we'll go to either this or here. Now for example, let's say we go here and this is forming an odd length cycle, right? So if we are coloring this with 0, we started with, this is 1 and this is again 0, and again we check the node that we are coloring to, for example at this point only, the node we are coloring to, it's having the same color as 0 now, right? And that's not that's not right in context of the Bipartite graph thing, so that would basically violate the property. So that's why we'll return false. And no, where are we returning false? If it's visited, if means if color of I is equal to -1 means it's not visited, else it's visited. Then we'll check else if color of I is equal to the color. If it's the same, means that's violating the property and will return false, or else will return true in all the other case. That's the only case of violating the property, and then we'll run this once. Fine, it works. We'll submit this. I hope you would have understood the approach. That was all for this video. Thank you.